Hello viewers, welcome back to the channel. In this video, we will discuss about forced vibration, resonance and different types of resonance under the chapter Simple Harmonic Motion and Oscillation of MACAUT BTech Physics syllabus paper code PH101 or 201. Before starting the class, if you have not still subscribed the channel, then please do subscribe the channel and like and share the videos with others. If you want to join my online classes and if you want to join my numerical problem solving classes, then you can contact me. The contact numbers and the descriptions are given in the background of my video. You can contact me through direct message. So let us start the class. Now what is forced vibration? When a periodic external force is applied to a system, the system starts vibrating with its own natural frequency, but the external force tries to impose its frequency to the oscillating system. Finally, the oscillating system vibrates with the imposed frequency or imposed force frequency and time period. So this is called the forced vibration. Now suppose a periodic force with a constant amplitude and frequency is acting upon a particle which is executing simple damped harmonic motion. Now there are two forces that are acting on that system. One is called the restoring force proportional to the displacement, which is restoring force which is proportional to displacement x, and secondly is called the retarding force which is proportional to the instantaneous velocity. Now we will find out the equation of motion of that system. So what would be the equation of motion of the system? Suppose m is the mass of that oscillator, then the equation of motion would be m d2x dt2 equals to minus of kx minus of b into dx dt, that is in proportionality constant b into instantaneous velocity dx dt plus applied force which is f cos omega t. Suppose for our case it is f cos omega t, which is the applied or imposed force or impressed force, which is external force. So this is the equation of motion, that is m d2x dt2 equals to minus kx minus b into dx dt plus f cos omega t, where omega is the frequency of the imposed force. Now if we divide both sides by m and take everything in the left hand side except the external force, then the equation of motion would be d2x dt2 plus b by m dx dt plus k by m x equals to f by m into cos of omega t. Similarly, the case of damped vibration, we can take b by m as 2a and k by m which is omega 0 square, where omega 0 square is the natural frequency of the system. So the second order differential equation takes the form, that is, now we denote it as x double dot, that is d2x dt2 plus 2a x dot plus omega 0 square into x equals to f divided by m into cos of omega t, where the symbols, all the symbols has their usual meaning, which I have already discussed in the damped vibration video. If you have some confusions regarding those symbols, then go back to that video of damped vibration. So this equation number is equation number 1. So equation 1 is a second order non-homogeneous differential equation. So we have to solve it. For solution আমাদের কি করতে হবে? Such type of second order non-homogeneous equation solution can be obtained from finding out the general solution. So general solution we can obtain by finding out the complementary function plus the particular integral function. So first of all we have to find out the complementary function for this differential equation 1. Now to find out complementary function, we have already done it in the damped harmonic vibration video. There we have taken as left hand side of the equation 1 as 0. So x double dot plus 2a x dot plus omega naught square x equals to 0. We take x equals to a e to the power of minus alpha t and we put it in this equation, and finally we get x for underdamped low damping case or oscillatory case as x equals to some constant d into to the power minus at into sine of omega prime t plus phi. Again another form is also we can get, which is x equals to d into e to the power minus at cosine of omega prime t minus phi. So both these are solutions for the displacement or the complementary function for the equation 1, which I have already discussed in the damped harmonic vibration video. There you can go and check it. These are the complementary functions that we got. Next we have to find out the particular integral. So we have to get the equation of motion in complex form. So we take two cases where external force is F cos of omega t, and second case external force is F sine of omega t, and also we take x1 and x2 be the displacements for case 1 and case 2. So the equation of motion for these two cases would be x1 double dot plus 2a x1 dot plus omega 0 square x1 equals to f by m into cosine of omega t, which is equation 2, and again we take x2 double dot plus 2a x2 dot plus omega 0 square x2 equals to f by m into sine of omega t, which is equation 3. Now we add equation 2 plus I into equation 3, and we obtain x1 double dot plus x2 double dot plus 2a x1 dot plus I x2 dot plus omega 0 square into x1 plus I x2 equals to f by m cos of omega t plus I sine of omega t. Now we take x1 plus x2, a new variable, that is capital X, which is complex in nature. So this equation will turn into capital X double dot plus 2a capital X dot plus omega 0 square capital X equals to f by m into this term would be e to the power I omega t. So we number it as equation 4. Now we have to solve this equation 4 to find expression for capital X, that is complex displacement. So let us take capital X equals to some constant a into e to the power I omega t. So if we put this value in equation 4, we will get minus a omega square e to the power I omega t plus 2a I omega e to the power I omega t plus omega naught square a e to the power I omega t equals to f by m e to the power I omega t. Or we take common a e to the power I omega t, we get omega 0 square minus omega square plus 2a omega into I, which is equals to f by m e to the power I omega t. So e to the power I omega t cancels out both sides, and finally we get a value of a equals to f by m whole divided by omega naught square minus omega square plus I into 2a omega. Now we have to rationalize the equation. After rationalizing, we get a equals to f by m omega naught square minus omega square minus I into 2a omega. In denominator it would be omega naught square minus omega square whole square plus 2a omega whole square. So আমরা কি ক্যালকুলেট করছি a এর ভ্যালুটা অ্যামপ্লিটিউড যে এটা নিয়েছি সলিউশনের ক্যাপিটাল x এর যে সলিউশন, for that solution we are calculating the value of a. Now we take omega 0 square minus omega square as b cos phi and 2a omega as b sin phi. So এই টার্মটাকে আমরা নিলাম b cos phi আর এই টার্মটাকে নিলাম b sin phi. So expression for a would be in numerator f by m into b cos phi minus I into b sin phi, and denominator it would be simply b square. We take common b from numerator and cancel out with the denominator powers 2. So finally we get f by m into it would be cos phi plus cos phi minus I into sin phi, and denominator it would be only b. So cos phi into I sin phi means e to the power minus I phi. So we write it as f by m into e to the power minus I into phi divided by b means root under of this expression. Omega naught square minus omega square whole square plus 2a omega whole square. This is value of a. Now we know omega naught square equals to k by m, which is natural frequency square, and 2a is b by m. So if we put this value here, we get amplitude as f by m e to the power minus I phi divided by under root it would be omega 0 square means k by m minus omega square whole square plus b by m omega whole square. So the numerator this m and these m will cancel out, and we will get finally f into e to the power minus I into phi divided by root under k minus omega square m whole square plus b square omega square. So this is the expression for a. Now we have to find out capital X, which is x equals to a e to the power I omega t. So put the value of a here, and we get x equals to f divided by root under k minus omega square m whole square plus b square omega square into e to the power I omega t minus phi. So this is the solution for capital X. Again we have to put the value capital X as x1 plus I x2 equals to f divided by root under k minus omega square m square plus b square omega square e to the power I omega t minus phi. Now we will expand e to the power I omega t minus phi in cosine and sine term. So we will get equals to f divided by this term k minus omega square m whole square plus b square omega square into, in bracket it would be cos of omega t minus phi plus I sine of omega t minus phi. Now comparing both sides, we get x1 equals to f divided by root under k minus omega square m whole square plus b square omega square into cosine of omega t minus phi, and similarly x2 equals to this term f divided by root under k minus omega square m whole square plus b square omega square into sine of omega t minus phi. So these are two solutions x1 and x2. So these are the particular integral functions. One is in cosine form, another one is sine form. So now we have to find out the general solution. So total general solution would be general solution x would be Cf plus Pi, that is complementary function plus particular integral. So we have complementary functions in terms of cosine form or sine form. Also we obtain particular integral in terms of cosine form or sine form. So if we take the cosine form, then the general solution for x would be d to the power minus at cos of omega prime t minus phi plus f cos omega t minus phi divided by root under k minus omega square m whole square plus b square omega square. This is general solution 1 if we take cosine form, and if we take the sine form, then general solution would be x equals to d to the power minus at sine of omega prime t minus phi plus f sine of omega t minus phi divided by root under k minus omega square m whole square plus b square omega square. So both these two equations are the general solution. One is in cosine form, another one is sine form. These are the general solutions for forced vibration under oscillatory motion or under damped motion. Here you have to remember that the forced vibration expression is this one. First part is due to damped vibration, due to under damping, and second part is due to forced vibration. Together both expressions form the general solution for forced vibration under damped or oscillatory condition. Now what are the resonance in forced vibration? So in case of forced vibration, when the external periodic force or external periodic force frequency is in period with the natural frequency of the oscillating system, then the system vibrates with the external periodic frequency. This is called the resonance. Here two types of resonances are present. One is called the amplitude resonance and second is called the velocity resonance. So in case of amplitude resonance, the amplitude of the forced vibration becomes maximum. As a result of that, the potential energy becomes maximum. So in case of amplitude resonance, amplitude becomes maximum, and as a result of that, potential energy becomes maximum. Now the expression for amplitude in case of forced vibration is A equals to F divided by under root K minus omega square M whole square plus B square omega square. This is the expression for amplitude. Now for amplitude to be maxima, the denominator part should be minima. to find the denominator minimum, we have to differentiate the denominator, that is dd omega of k minus omega square m square plus b square omega square. That should be 0. So we get 2k minus omega square m into minus 2 omega m plus 2 b square omega equals to 0, or these 2 cancel out and also this omega cancel out. We get b square equals to 2 m k minus omega square m, or k minus omega square m equals to b square by 2m, or omega square equals to k by m minus b square by 2m square. So this is the expression for frequency for amplitude resonance. So this is the expression for frequency in case of amplitude resonance. So we have to put this omega square value in the equation of amplitude. So put omega square value in amplitude resonance. So we get we have to put it here. So we have to put the value of omega square here, and we will get the amplitude, maximum amplitude for amplitude resonance. So we finally get A max, that is equals to F divided by k minus omega square m, that means k by m minus b square by 2m square into m square plus b square into omega square, that is k by m minus b square by 2m square. Or we will get f divided by b to the power 4 divided by 4m square plus b square k by m minus b to the power 4 by 2m square, or f divided by b into k by m minus f or we get f divided by b into k by m minus b square by 4m square whole to the power half. So this is the amplitude resonance. So this is the expression for maximum amplitude for amplitude resonance. Now if we plot the amplitude versus frequency in a graph, then it will be like, for in case of amplitude resonance, the graph would be like this one. So along y axis amplitude has been plotted and along x axis frequency has been plotted. So So at a resonant condition, the frequency omega becomes omega max, which is the peak of these curves. So here different k values or different damping factors has been considered. For different damping factors, we can see how the amplitude resonance or the amplitude changes with frequency. So for different k values, for increasing k values, we can see that amplitude is decreasing. Here the damping is increasing. So this is the graph where we can see that how the amplitude, in case of amplitude resonance, how the amplitude changes with frequency for different increasing damping cases. So for values k0, this one is the graph. For k1, this one is the graph. K2, k4 and k5. So with increasing damping, the amplitude decreases with frequency. So this is the curve for or graph for amplitude versus frequency for different damping values. Now in case of velocity resonance, that is second type of resonance in forced vibration, here what happens, the velocity becomes maxima in case of resonance. So that means velocity maximum means kinetic energy would be maximum. The kinetic energy as well as velocity of the oscillating system becomes maximum. Now we will calculate the expression for velocity resonance. So the expression for displacement in case of forced vibration which we obtained is F equals to F divided by root under of k minus omega square m square plus b square omega square into cosine of omega t minus phi. We take the cosine form. Now we have to calculate velocity. So velocity would be dx dt. So that would be minus f omega into sine of omega t minus phi all divided by this under root term k minus omega square m square plus b square omega square. So here velocity amplitude is velocity amplitude is magnitude is f into omega divided by this term k minus omega square m square plus b square omega square. So this is the velocity amplitude part. So here similarly we have to calculate the maximum value. Now this velocity amplitude would be maxima when the denominator is minima. So the denominator term, this term would be minima, and the denominator would be minima when this term, bracketed term k minus omega square m becomes 0. So this will become minima when this becomes 0, or omega becomes k by root under k by m, which is also the natural frequency. So in case of velocity resonance, the frequency of the oscillating system would be equal to the frequency of the imposed force. So at resonance, omega becomes equals to omega 0. So in that case, velocity amplitude would be so this term is 0, that means f omega divided by root under b square omega square, which is equals to f by simply b, f by b. So in case of velocity resonance, the velocity amplitude is simply f by b. So one thing you can see from these results, from the amplitude resonance as well as velocity resonance, that at resonance condition, both the amplitude resonance part and the velocity resonance parts are independent of frequency. And in 2020 McCourt BTech question paper, this question came, that is starting from the equation of motion and after solving it, so that for a forced oscillator in the steady state, displacement amplitude at low frequencies, the displacement velocity amplitude at velocity resonance are independent of the frequency of the driving force. So this solution I have already discussed in this lecture. For different damping values, this would be the graph for velocity resonance, velocity amplitude versus frequency graph. So this also came in the question 2020 of McCourt BTech physics syllabus, of McCourt BTech physics question paper. So this also came as a question in 2023, that draw the graph for displacement amplitude and velocity amplitude against frequency of for a given force for defined values of damping coefficients. So those graphs you have to, this graph and this graph you have to draw. So this is the end of today's video. See you in the next video. Till then, bye.